This is number 2 from the practice exam. It asks us to find the conditions for periodicity for continuous time and discrete time functions. So A is given as x of t equals 5 sine 3t plus 1. And you can, of course, find the formal statement of periodicity for a continuous time function in the lectures or midterm review, but it's basically any function where if you take any tau and advance the function, you get the function back. So basically, the formal statement, just to be perfectly clear, is for all t, there is a tau such that x of t plus tau equals x of t. So for our specific function, x of t equals 5 sine 3t plus 1, we need to test this, so let's jump right in. And we can write this using a trigonometric identity as 5 times sine 3t plus 1 times cosine tau plus cosine 3t plus 1 times sine tau, and the trigonometric identity is of course going to be sine A plus B equals sine A cosine B plus cosine A plus times sine B. In this case, A is equal to 3t plus 1 and B is equal to tau, and you can see that if you just multiply out the phase here, you get 3t plus 3 tau plus 1. Sorry, we're missing a 3 up here. It's going to be 3 tau. So that's the phase. Okay, so let's get rid of that here. And now we can see that we have 5 times sine 3t plus 1 cosine 3 tau plus cosine 3t plus 1 sine 3 tau, and by our periodicity condition, we need this to be equal to the original function, which is just 5 sine 3t plus 1. Okay, so by inspection, you can tell that cosine 3 tau needs to be equal to 1, and sine 3 tau needs to be equal to 0, because we need to get rid of this completely. if this is going to have any chance of being true. So sine 3 tau equals 0. So this is a system of equations, and hopefully you recognize that for this to be true, cosine 3 tau equals 1, that is, then 3 tau needs to be a multiple of 2 pi. And we'd write that as 2k pi, where k is, 0, 1, 2, etc. And this condition will also satisfy this, because sine 2k pi is always going to give you 0, assuming k is an integer. And that's the important part here. K is constrained to be an integer. If k was, say, not constrained to be an integer, it could be a rational or irrational number. This is not necessarily going to be a true statement. Okay, so then we can see that the period for this function is just 2k pi divided by 3. And we would write shorthand, we would say k is in z, and this z symbol right here is just the symbol for the set of integers. You'll probably see that at some point if you haven't seen it yet. And we could have actually picked this period out directly from x of t without going through all of this, just by writing that well, let's not go into that since we already did it this way. Okay, so B asks us to find the period of a discrete function, and they also want us to list the conditions. So I'm going to state this one formally because it's a little more nuanced. So a discrete time function is periodic if for all n there is a capital N, which is going to be our period, such that, that's the such that symbol, that's what it means, x of n plus n is equal to x of n. Okay, so we've been given the function x of n equals cosine pi over 4 times n. Okay, so let's go about proving this. So we are going to write, first off, we're going to write x of n this way. And the way I'm writing it here is, of course, Euler's famous identity. Hopefully you know that by now. But if not, that's just cosine theta plus j sine forgot a j there, sorry. Theta equals e j theta. Just makes that a little more clear. Okay, so Now we can write x of n plus n is equal to the real part j pi over 4 n plus n. Okay. We can also write that as x of n plus n equals real e j pi over 4 times n times e j pi over 4 times big N. And our periodicity condition is, of course, that this is equal to x of n, which is just equal to real part of ej pi over 4 n. Okay, since we're considering the real parts of both these functions, and they're similar, we can just kind of neglect this for a while, and we can just write that ej pi over 4 n times ej pi over 4 big N must be equal to ej pi over 4 little n. Okay, so these are going to cancel, and we can see that ej pi over 4 big N must be equal to 1. Okay, so the only time this is going to be true is if pi over 4 big N is equal to some multiple of 2k pi again. And that's because ej 2k pi is equal to 1, where k is some integer. Okay, so now we can write that n is equal to, the pi's cancel, 8k, where k is an integer. And that's our condition for periodicity for this function. X of n equals cosine pi over 4 times n. It's periodic with the fundamental period n naught equal to 8, and has other periods given by this right here. And we could have found that this condition of periodicity was satisfied immediately from the function by writing it as cosine pi over 4 times n, and a discrete time function is going to be periodic if and only if omega naught, only if 2 pi divided by omega naught is equal to n divided by m, and n divided by m is going to be a rational number. If it's a rational number, if and only if it's a rational number, is x of n going to be periodic. And if you're unsure of what I mean by rational number, basically it's going to look something like this. It's got to look like that. If it has, not that you would run into this, but if it was, say, e divided by 3, that's not a rational number. E is an irrational number. If there's a pi in it, pi divided by 2, no, pi is an irrational number. So n divided by m has to be a rational number. Pi is irrational. E is irrational. You can think of other ones. Okay, that's it for number 2.